This lesson is part 1 of section 10.1. I think you guys are going to like this section because it's right triangle applications. So you've done a lot of this already in geometry, so this is a lot of review for you. But our main objectives for today are going to be to solve a right triangle using trig, specifically in context to a word problem, and we are also going to find the area of a triangle and other regular shapes. Okay, let's begin here with questions 1 and 2. Now the directions say to solve the right triangle. Now what that means is you're just going to find the missing side lengths or angles in the triangle. Now in example 1, the missing angle is pretty easy to find. We're just going to subtract, the angles of the triangle, add up to 180, so we know that that must be 30 degrees. To find x and y though, we need to use SOHCAHTOA. Okay, we're going to use that old saying, SOHCAHTOA. Remember how that one goes? Some old hag caught another hag tripping on acid. You know how the old saying goes. Obviously, I don't recommend that you trip on acid, but, it's an old saying. Okay, but anyhow, let's find x and y. Now, I'm going to ignore that 30 degrees here, and we're just going to focus on this 60 degrees. Now, from this angle's viewpoint, we have the adjacent side and we have the hypotenuse. So I can set up an equation here using cosine. Since I have adjacent and hypotenuse, I'll use the cosine. So the cosine of 60 degrees is equal to x over 20. Now if I want to solve for x, I multiply by 20 and I have x equals 20 times the cosine of 60 degrees. Now I can simplify this further. I don't need a calculator for this because I know that the cosine of 60 degrees is 1/2. So I have x equals 20 times 1/2, so I end up with 10. Now to solve for y, I have the opposite and I have the hypotenuse, so this time I'm going to use sine. So I have the sine of 60 degrees is equal to y over 20. So to solve for y, I multiply by 20. And I have 20 times the sine of 60 degrees. And again, I can evaluate this without the use of the calculator. This is going to be 20 times the sine of 60 degrees. That's going to be root 3 over 2. So I end up with 10 root 3. Now this is also consistent with those, right triangles, those special right triangles when we dealt with a 30, 60, 90 triangle. But this is just another method. You can now use your trig values in order to calculate the exact value for the cosine of 60 and the sine of 60. Now in number 2, I'm asked to solve for the angle measures here in this triangle. And from this viewpoint, I actually have all three sides, so I could choose sine, cosine, or tangent. I'm going to use tangent just because we haven't used that one yet. So if I'm going to take the tangent of theta, I know that that's equal to the ratio of 7 over 24, the opposite over the adjacent. So if I want to solve for theta, I need to take the inverse tangent of both sides. So I have inverse tangent of 7 over 24 is equal to theta. Now this is an exact value. Obviously I could type that into my calculator to find its approximation, but if I wanted to find beta, beta has to be 90 minus theta. So in other words, beta is equal to 90 minus the inverse tangent of 7 over 24. This would be another exact answer to describe beta in terms of theta. So this is how we're going to now solve using, or in context to word problems. Okay, so when you're solving a right triangle trig application problem, you always want to make sure that you're setting up the picture accurately. So here we have a ladder leaning against a wall. So I would right away try to depict this. Obviously, this side here represents the wall, and here is the ladder. Okay, the base of the ladder here is 1.7 meters from the base of the building. So we want to accurately describe the side length that they're giving us. From the wall to the ladder, so this segment here from the wall's base to the ladder is 1.7. And the ladder makes an angle of 74 degrees with the ground. So here's the angle formed with the ground and the ladder, so that's 74 degrees here. How far from the ground is the top of the ladder? So we're asked to find this segment here, not the length of the ladder, but how far from the ground is the top of the ladder. So we really want to know basically how far up the wall that ladder is positioned. So this is my missing value here. So from the viewpoint that I'm given, the 74 degrees, I have the opposite side and my adjacent side. So I'm going to need to use the tangent function here. So the tangent of 74 degrees is equal to x over 1.7. So to solve for x, I end up with 1.7 times the tangent of 74 degrees. So this is the exact answer here. And you could use the calculator to find your approximate value. Okay, our next trig application problem deals with something called the angle of depression. So I want to review this specifically with you, as well as an angle of elevation. But anyhow, this problem says that from the top of a lighthouse, 210 feet high, you look down and you see a boat and an angle of depression of 27 degrees. We're asked to find the distance from the boat to the foot of the lighthouse, okay? So we're assuming now that the lighthouse was built at sea level. So that's kind of important here because otherwise that would affect our vertical height here. But anyhow, you're looking down, right, at this boat. Okay, now an angle of depression is actually not this angle inside here. That's what most students will mistakenly write. The angle of depression is always formed with a horizontal line. So we look at this horizontal line and we're looking down from that. That's why it's a depression, downward. And this is the angle measure inside here that's 27 degrees. Now that angle measure is equivalent to the angle down here way at the base. That's also 27 degrees. And you can use, you know, your angles, your alternate interior angles here because these are parallel lines, right? That's parallel to this horizontal here. But that's, you know, a little bit more geometry than I need to get into right now. So anyhow, what you're really looking for is this angle measure here, which is 63 degrees because we're going to take 90 minus the 27 here. So in our right triangle, we're actually interested in this 63-degree angle, unless, of course, you were to come down here and write that in as 27 degrees. But I like to just do the 63 degrees at the top. All right, so that's what it means by an angle of depression. So just to give you a little bit of notes that you can write in there. An angle of depression is formed downward from a horizontal. Okay, and an angle of elevation is formed upwards from a horizontal. Okay, because to elevate means to go up. So hopefully that makes intuitive sense to you as well. So anyhow, let's work on actually solving this problem. Now the top of the lighthouse is 210 feet high, so really that's giving us the height of this triangle here, 210, and we have this 63 degrees up here. We are supposed to find the distance from the boat, which is here, to the foot of the lighthouse here. So we're finding this segment. So if we look, we have the opposite and the adjacent. So we're going to again use tangent. So you have the tangent of 63 degrees is equal to x over 210. And I'm going to use, I'm sorry, not use my calculator, but I'm just going to use an exact answer here. 210 times 60, the tangent of 63 degrees is equal to x. So that's the exact answer, and of course I can type that into my calculator to find the approximate value. All right, in the next portion of our lesson, we're actually going to derive a brand new formula for the area of a triangle. So I want to start with the one that we are so familiar with because we've been using it since like the 4th grade here. Area equals 1/2 base times height. So this formula requires me to know the base and the height of a triangle. But let's say I am not given the height of a triangle and instead I'm given an angle measure. So this angle measure is going to be in a particular location. It must be between two known side lengths. Okay, so we call that the included angle. It's between two known side lengths. Now, if I want to express this angle measure here in terms of the sides that I am given, I could say that the sine of theta, because I could break this down into a smaller right triangle, the sine of theta is equal to the opposite side h over a. And because I can now solve for h, I can say that h is equal to a times the sine of theta. So making that substitution here, I no longer need to know the height of a triangle. I can use 1/2 times the base times, again making the substitution, a times the sine of theta. And if I just kind of mix that up a little bit, we get this brand new formula, 1/2 times a times b times the sine of theta. The theta here, again, is the included angle between sides A and B. Okay, so if A and B are two lengths of two sides of a triangle and theta is the angle included between those sides, then the area of the triangle is given by 1/2 times A times B times the sine of theta. So it is the product of A and B, those two sides, divided by 2, multiplied by the sine of theta. Okay, let's try number 5 here, which asks us to find the area of this triangle. So notice that I'm missing the height of this triangle. If we were only using the formula area equals 1/2 base times height, we can't get anywhere with this, so we wouldn't be able to find the area. However, we can completely bypass the fact that we're missing the height because we have two sides of a triangle and we are given the included angle. So again, if this 3 here might have been over here, we would not be able to find the height using this particular formula. But because we have two sides of a triangle and the included angle, we know that we can take the product of those two sides and take half of that product and then multiply it by the sine of that included angle. So I'm going to take 1/2 times 3 times 12, so 1/2 of 36 times the sine of 60 degrees. So I have 18 times the sine of 60, which is root 3 over 2, and that will simplify then to 9 root 3, and this is units centimeters squared. So we have 9 root 3 square centimeters for the area of this particular triangle. Okay, now we're going to extend the idea of finding the area of a triangle when you're missing a height to finding the area of a regular hexagon. So here I'm going to have to review a bit of geometry with you. Now the fact that it's a regular hexagon means that it's both equiangular and equilateral, so I can mark each of these side lengths the same. Okay, so now I have congruent chords, right? So I have congruent chords here. Well, those congruent chords form congruent arcs. Now, if those arcs are congruent, they have the exact same measure, okay? So it's a lot of logic here using geometry concepts, but each of those arc measures must be the same. Now, those arc measures directly relate back to the central angle here. So if this has a central angle of x degrees, then this arc measure here is also x degrees. So if I want to know what theta is, okay, since theta here is my included angle between these two sides, I need to find that in order to find the area of this particular triangle. So to find theta, what I will do is take 360 degrees and divide that by 6, since I have 6 congruent arc measures. Okay, that will give me the arc measure of 60 degrees, which correlates back to the central angle of 60 degrees. So I know now that theta here is 60 degrees. So now that I know that theta is 60 degrees, I can find the area of this triangle. Hopefully I'm not moving too fast here with all this geometry review. But once I have the area of that triangle, I can then multiply it by 6 because I have 6 congruent triangles here within this regular hexagon. So let's find now the area of this particular triangle. Remember, it's going to be the product of the two included sides. So half of that is 20 times 20 divided by 2. And then times the sine of this particular included angle, which is 60 degrees. So I have the area equals 1/2 of 400, so 20 times 10 gives me 200. So I have 200 times the sine of 60 degrees. Now the sine of 60 degrees is root 3 over 2. So I end up with 100 root 3. Now this is, you got to be careful because this is only the area of this little triangle here. We need to multiply that by 6. So we end up with a total area for this particular hexagon of 600 root 3, and that's units squared since I didn't give you units. Now, your book is going to have a little bit trickier problems. Like they might ask you for just the area of this particular segment here. So this is a tiny little portion of the overall circle. And in this case, what you would need to do is find the area of this sector, which you are now more than capable of finding. So find the area of this sector, and then you would have to subtract out the area of the triangle. Okay, so from here it's just a matter of problem solving. Okay, so that was kind of a short one. Tomorrow we're going to do some more right triangle apps, but that's the end of the lesson. I'll see you guys in class tomorrow.